Microwave spectroscopy or rotational spectroscopy. Rotational spectroscopy is concerned with the measurement of the energies of transitions between the condensed rotational states of molecules in the gas phase. The spectra of polar molecules can be measured in absorption or emission by microwave spectroscopy. A molecule in the gas phase is free to rotate related to a set of mutually orthogonal axes of fixed orientation in space centered on the center of mass of the molecule. For example, this is water molecule. It can rotate about three mutually perpendicular axes. This is the C2 axis and it is also the Z axis. So it can rotate about the Z axis and it can rotate about the Y axis and it can also rotate about the X axis. And the rotation about the C2 axis or Z axis is shown here. Free rotation is not possible for molecules in liquid or solid phases due to the presence of intermolecular forces. Hence, rotational energy levels are not well defined in the case of liquid and solid phases, and rotation spectrum can be obtained only in the gas phase. Classical rotation of a diatomic molecule. Angular momentum can be considered as a rotational analog of linear momentum. The expression for linear momentum is P is equal to m into v, where m is the mass and v is the linear speed. And the expression for angular momentum is L is equal to I omega. Here I is the moment of inertia and omega is the angular speed. The moment of inertia I of a rigid body determines the torque needed for a desired angular acceleration about a rotational axis. The energy of a rotor is given by the expression E is equal to L square by 2I. The angular velocity is a vector quantity and describes the speed of rotation and the orientation of the instantaneous axis about which rotation occurs. The direction of the angular velocity vector is perpendicular to the plane of rotation in a direction which is usually specified by the right-hand rule, and in this case counterclockwise rotation takes place and the vector points up. Rigid rotor model. Here the two nuclei are joined by a weightless rod. For simplicity, we consider only rotation motion of a rigid diatomic molecule. A diatomic molecule can rotate around a vertical axis. Here Cm is the center of mass and R1 or Ra is the distance of the first atom from the center of mass, and Rb or R2 is the distance of the atom from the center of mass, and the internuclear distance R0 is equal to R1 plus R2. For rotation about center of gravity, we can write the expression m1r1 is equal to m2r2, and we can write R2 as R0 minus R1 because R1 plus R2 is equal to R0. So expanding M2 R0 minus M2 R1 and bringing this term to the left side, we have M1 R1 plus M2 R2 is equal to M2 R0. Taking R1 outside, we get R1 into M1 plus M2 is equal to M2 into R0. So we may write R1 is equal to M2 R0 divided by M1 plus M2. Similarly, if you write M2 R2 as M1 into R0 minus R2, we get a similar expression. R2 is equal to M1 R0 divided by M1 plus M2. The moment of inertia I is a measure of an object's resistance to changes in its rotation rate. It is a rotation analog of mass. The moment of inertia about the center of mass is given by the expression m1r1 square plus m2r2 square. And instead of m1r1, we may write m2r2. So m2r2 into r1. And instead of m2r2, we may write m1r1. So m1r1 into r2. And taking r1 and r2 outside, we may write r1 r2 into m1 plus m2. But we have already derived this expression r1 is equal to m2 r0 divided by m1 plus m2, and r2 is equal to m1 r0 divided by m1 plus m2. So substituting values of r1 and r2 in this expression, we have m2 r0 divided by m1 plus m2, m1 r0 divided by m1 plus m2 into m1 plus m2. So 1 m1 plus m2 term get cancelled because it is common both in the numerator and denominator. And here r0 into r0 is equal to r0 square. So we have the expression for moment of inertia m1 plus m2 divided by m1 plus m2 into r square. And this m1 m2 divided by m1 plus m2 term may be replaced by mu. Here mu is called reduced mass. So we have the expression moment of inertia I is equal to mu into r0 square. Now the angular momentum L is given by the expression I omega. According to results from quantum mechanics, the angular momentum is quantized and its values are given by Lz is equal to h by 2 pi into square root of j into j plus 1, where j is called rotational quantum number and it has values ranging from 0, 1 to etc. Microwave spectroscopy. Incident electromagnetic waves can excite the rotation levels of molecules provided they have an electric dipole moment. The electromagnetic field exerts a torque on the molecule. The spectra for rotation transitions of molecules typically occurs in the microwave region of the electromagnetic spectrum. Homonuclear diatomic molecules such as hydrogen, oxygen, nitrogen, chlorine, and heteronuclear polyatomic molecules like CO2, CH4, BO3 have zero dipole moment. They are non-polar molecules. They have zero change of dipole moment during rotation. Hence, no interaction with the radiation takes place, and hence such molecules are microwave inactive. Heteronuclear diatomic molecules such as HCl, HF, CO, H2O have permanent dipole moment. They are polar molecules, and the change of dipole moment occurs during rotation. Hence, interaction with the radiation takes place in these cases, and therefore heteronuclear diatomic molecules are microwave active. Rotation of HCl molecule and the dipole moment changes during rotation. HCl molecule is a polar molecule. Chlorine atom is more electronegative than hydrogen, and it attracts the shared pair of electrons towards it, and hence chlorine atom gets a partial negative charge and hydrogen atom gets a partial positive charge. Dipole is a vector and its direction is taken as from positive to negative pole. So the orientation of the dipole is like this. It points downwards. Now when HCl molecule rotates clockwise, after 90 rotation, the orientation of the molecule is like this, and the orientation of the dipole is like this. Another 90 rotation, orientation becomes like this, and the dipole points upwards. The variation of the vertical component of the dipole is represented in this graph. So during rotation of HCl molecule, there is a periodic variation in the dipole of the HCl molecule. Rotation spectra of rigid diatomic molecule. The rotation energy is also quantized. By using Schrodinger equation, the rotation energy levels allowed to rigid diatomic molecule is given by, first we know E is equal to L z square by 2I, and the angular momentum values are given by h by 2 pi into square root of j and j plus 1. So substituting the value L is set in the expression for energy, we get the energy of a rigid diatomic molecule equal to h square by 8 pi square I into j into j plus 1. Here j is the rotation quantum number and it has values ranging from 0, 1, 2, 3, etc. We can also express the energy of the radiation in terms of the wave number. We know E is equal to h nu and replacing frequency by c by lambda, h into c by lambda. Now here 1 by lambda is called wave number and it is represented by the symbol nu bar or epsilon. So I have written here h into z into nu bar or h into z into epsilon. So by dividing energy by this term by hc, we get wave number. So E by hc is equal to wave number. Now by dividing the expression for the energy by the term hc, we get the energy of the radiation in terms of wave number as epsilon j is equal to h divided by 8 pi square I into z into square root of j and j plus 1. Now this term may be replaced by b. So we may write epsilon j is equal to b into j into j plus 1. Here b is a constant for a given molecule and it is called rotational constant. By substituting the values of j, substituting the values j equal to 0, 1, 2, 3, etc. in the expression for wave number, we get the energy of the first rotation level epsilon 0 as equal to 0, second level as equal to 2b, third level as equal to 6b, and so on. Energy levels of a rigid rotor are represented in this figure. Here this is the lowest rotation level with the j equal to 0 and energy 0. That means the molecule is not rotating. The molecule is stationary. It is not rotating and this rotation energy will be 0. And next level j equal to 1 has energy 2b. And next level j equal to 2 has energy 6b. And next level j equal to 3 has energy 12b. Now let us calculate difference in energy between two adjacent levels. Here energy difference between j equal to 1 level and j equal to 0 level is 2b. And j equal to 2 level and j equal to 1 level is 4b. And j equal to 3 level and j equal to 2 level is 6b. Now in vibration spectroscopy there is a selection rule which says delta j should be equal to plus or minus 1. Here delta j is the rotation quantum number of the final state minus rotation quantum number of the initial state. So this selection rule says that if a molecule is originally in the level j equal to 0, then it may absorb microwave radiation and get excited to a level with j equal to 1, because in this case delta j would be plus 1. It cannot get excited to a level j equal to 2 or j equal to 3, because in these cases the delta j value would be plus 2 or plus 3. Now if a molecule is originally here, then it may absorb radiation and get excited to level j equal to 2 and not to j equal to 3. Now if a molecule is here, then it may undergo emission to a level j equal to 0 in this case, because in this case delta j is minus 1, which is allowed by this selection rule. Now let us see the rotation spectrum of any molecule. So in the rotation spectrum we get a series of equally spaced lines, and the first line is corresponding to j equal to 0 to j equal to 1 level, and it would appear at 2b. The next peak corresponds to a transition from j equal to 1 to j equal to 2, and it appears 4b. And next one appears at 6b, next one 8b, 10b, 12b, and so on. Now the difference between two adjacent peaks would be 2b. 4b minus 2b, 2b, and the 6b minus 4b, 2b. So the difference between two adjacent peaks in rotation spectrum would be always 2b. The wave number change associated with a rotation transition from a level with the quantum number j to a next higher level, j plus 1, is given by. So for calculating this, we know this is the wave number of any rotational, b equal to j into j plus 1. So to calculate the difference, we assume that transition takes place from the level j to j plus 1. So first we calculate the energy of j plus 1 level. So here instead of j, we have to substitute j plus 1.
So B into J plus 1 to J plus 1, then this one plus 1. Then the energy of the level J, that is B into J plus 1. So difference gives 2B into J plus 1. So here J is the level from which transition occurs. So summary. Microwave spectroscopy is concerned with the transitions between rotation levels of molecules. And the moment of inertia is given by the expression m1 m2 divided by m1 plus m2 into r0 square. Here m1 m2 divided by m1 plus m2 is the reduced mass represented by the symbol mu. And energy levels of a rigid diatom rotor is given by the expression epsilon j is equal to b into j plus 1, where j is the rotational quantum number and b is the rotational constant, and it has units in centimeter inverse, and it is given by the expression h divided by 8 pi squared I into c. Here I is the moment of inertia and c is the velocity of light, h is the Planck's constant. And selection rules. A molecule to absorb microwave radiation, it must possess a permanent dipole, and a delta J should be equal to plus or minus 1. And space in between the lines in the rotated spectra of a rigid diatom molecule is constant, and it is equal to 2b. Here, this is the rotational spectrum of HCl molecule. We see a series of equally spaced lines, and the difference between two lines gives the value 2b. So it is here it is found to be 21.2 centimeters. That is the value 2b, and b will have a value 10.6 value. So if you know the value b, then we can calculate moment of inertia. And from the moment of inertia, the expression you can calculate r0, the equilibrium bond distance. So here is the calculation. First we have to calculate the reduced mass m1 m2 divided by m1 plus m2. Remember, m1 is the mass of a single hydrogen atom. Here this 1.008, that is in grams, it is the mass of 1 mole of hydrogen atom. 1 mole of hydrogen, that also it is in grams. So we have to calculate the mass of a single hydrogen atom in kilograms. So here is the calculation. m1 1.008 into m2, that is the mass of chlorine atom, is 34.9688 divided by 1.008 plus 34.968. That is the reduced mass in IU. To convert it to kilograms, you have to divide by Avogadro number and also divide by 1000. So you get a factor like this. You get a factor. So this is the reduced mass of HCl molecule in kilograms. So the whole calculation. So to calculate B, that is expression. Sorry, to calculate R0, that is Coulomb distance. R0 will be equal to h divided by 8 pi squared mu Cp. Here mu we have already calculated, and this is the values of the mu, and h is the Planck's constant, and c is the velocity of light, and v is the rotation constant obtained from the rotation spectrum. So if you calculate like that, you will get a value of 1.274553 into 10 raised to minus 10 meters. And this is the rotation spectrum of carbon monoxide. And again we get a series of equally spaced lines, but their intensities are not same, they are different. Now in this session we will see why intensities of spectral lines in the rotation spectrum are different. The intensity of rotational spectral lines depends on the population of energy levels. And the population energy levels depends on two factors. One is Boltzmann distribution, and another is number of degenerated energy levels. The Boltzmann distribution. Suppose number of molecules in the first state is N0 and the number of molecules in any higher state is Nj. Then the ratio of populations Nj by N0 is given by the Boltzmann distribution law, and it is equal to e raised to minus Ej by kT. Here Ej is the difference in energy between the level J and 0. and K is the Boltzmann constant and T is the temperature in Kelvin. So we may write this expression E, instead of E we may write h nu, and by converting wave number it is equal to h into z into nu bar. But we know the value nu bar. It is equal to b into j into j plus 1. So by substituting this value we get an expression like this. It is minus b into j into j plus 1 hc divided by k into t. Here this Boltzmann distribution is plotted against the rotation quantity number j, and we can see that this value, the Boltzmann distribution value, has the highest value for j equal to 0 level, and as the value j increases, it decreases. Now this plot is a plot of degeneracy. Degeneracy of level is given by 2j plus 1, and we know when j value increases, degeneracy will also increase. So there is a linear increase, and this is the plot of degeneracy of a level against the rotation quantity number j. So by multiplying this, the degeneracy factor, that is 2j plus 1 into with the Boltzmann distribution, we get curves like this. So these curves depends also on the temperature. The shape of the curve depends also on the temperature. So when the temperature is 300, and if the value is B value is 10.6 centimeter inverse, then the maximum occurs around here. So from this figure it's clear that the maximum population occurs in this case around rotation quantity number 3. Now when the temperature increases, the maximum shifts to higher values. So this maximum appears around 5, rotation quantity number 5. This shows that when the temperature is 300, then maximum population is in the rotation level with the j equal to 3, and if the temperature is 1000, then maximum population is in the rotation level with the quantity number 5. We can calculate theoretically the rotation level in which there is a maximum population. We know the exponential population is this one, and by differentiating with respect to j and setting equal to 0 for a maximum, we get an expression like this. J maximum is equal to square root of kt by 2hcb minus half. Here J max is the rotation quantity number of the level in which maximum population occurs. K is the Boltzmann constant, T is temperature in Kelvin, and H is the Planck's constant, C is the velocity light, B is the rotation constant. Bond lengths and rotation constants of some diatom molecules are given here. First one is H2+. It has a bond distance of 1.06 angstroms and a rotational constant of 29.8 centimeter inverse. And for H2 it is 0.74138 and rotational constant is 60.8. For D2 the bond distance is 0.74154 and rotational constant is 30.4. So by comparing these values we see that for hydrogen and D2 there is not much change in the bond distance, but the B value is reduced to half when we go from H2 to D2. This is due to change in the reduced mass of the substances. Effect of isotope substitution. Here this is the rotation spectrum of HCl. And if you look at each peak closely, we see that each peak is actually a doublet. It consists of two peaks. One is having higher density and another is having lower density. The peak appearing at higher wave number is corresponding to HCl35 and the other peak is corresponding to HCl37. The values of B for these two isotopes are different. The value of B is inversely proportional to reduced mass. So when the reduced mass increases, the B value decreases. That is why the B value for HCl37 appears at a lower value. Now effect of isotopic substitution on carbon monoxide. On changing from carbon monoxide with the C12 isotope to carbon monoxide with the Z13 isotope, the atomic mass increases, so B decreases because B is inversely proportional to I, so energy levels become closer. So this is the energy level diagram for 12CO and this is the energy level diagram for 13CO. So effect of isotopic substitution on the spectra. For 12CO, the B dash value is 1.9 to 118, and for 13CO, the value is 1.83669. So the ratio of this B dash to B double dash gives value of mu double dash to mu dash, and it is 1.046001. Now we can calculate rotation spectroscopy to find the isotopic mass of 13C. Here we assume that we know the isotopic masses of 12C and oxygen. For 12C, the atomic mass is 12 atomic units, and for oxygen it is 15.994. From rotation spectrum, we get a B value of 12CO as 1.9 to 117, and for 13CO it is 1.836685. So B is inverse proportional to mu, that is reduced mass. So ratio of reduced mass of 13CO and 12CO will be equal to ratio rotation constants of 12CO and 13CO, and it is 1.04600. And from this we can calculate the isotope mass of 13C. From comparison of rotation energy levels of 12CO and 13C, we can determine the isotope masses accurately to within 0.02% of other methods for atoms in gas molecules, and we can also find isotopic abundances from the absorption relative intensities. So this is an assignment. The first rotation line in the rotation spectrum of carbon monoxide is observed at 3.84235 cm. Calculate rotation constant B and bond length of Cu. The relative atomic weight of C is equal to 12 and oxygen 15.994, and absolute mass of hydrogen is equal to 1.67343 into 10⁻⁻27 kg. Thank you.